Hello everyone, welcome to my YouTube channel Code with Aryan and to the Data Structures and Algorithm course in Java. And as we have seen in the previous lectures, we have done time complexity using recurrence relations and also many running time calculations. So our today's topics are comparison of functions, asymptotic notations, and best, worst, and average case analysis. So the first topic is comparison of time and space functions. So for example, as we have seen previously in our running time calculations and other examples, whenever we got time functions such as a constant value, the order was O of 1 because the power of n was 0 here. For a linear function like this, the order was order of n, and for this quadratic function, the order was order of n square or big O of n square, which we usually say. For this it was order of n cube. For this, if we calculate and simplify, this is a recursive function, and for this we get order of n. For this we got order of n 2 power n. This is same as the previous example in the recursion video, and this one we get order of n log n. If we simplify it, we can get this. So these functions which we write inside the brackets of O are called the classes, and we determine the classes in a particular manner in which we can see which takes the lesser time and which takes the higher time, and hence we compare an algorithm using the amount of time it takes. So as we know, the algorithm which takes lesser time will be better and more efficient. So we say that these are called classes, and these are the ones which are taking lesser time is better, and the ones which are taking higher time is slower and less efficient than these ones. So these are the classes in which we define the order, and we say that this constant takes lesser time, log n takes more but less than root n, and similarly it increases the time in this order, and polynomial takes lesser time than exponents. So we can take it as an example. We can take an example to see how it works. So for example, when n is like here, this just simply means that as n increases, like n is the input, so how our time increases with the input. So we'll see this here. As n is 1, n square will be 1, n cube will be 1, 2 power n will be 2, and log n will be 0 if it's log base 2n, for example. So let's take n equal to 2, n square will be 4, it will be 8, and this will be 4. But in this table we can see 2 power n should have higher time than n square, but here we are seeing that still it is like same, or maybe or n cube, sorry, not n square, n cube. So we should see that 2 power n should have higher time than n cube, but here we can see for the first time it was higher, but then it is lower. So how does this work? Wait, and just let's increase the number of inputs. So for this for n equal to 2, log n will be 1 because the base was 2. So let's take n equal to 4. For n equal to 4, n square will be 16, n cube will be 64, and 2 power n will be 2 power 4, which is 16. Still it is lower, and this log n will be 2. Now let's take n equal to 8. So it will be 64, this will be 256, sorry, this will be 512, and this will be 256. Still we can see this is lower. Now and this will be 3. Now let's take n equal to 10. For 10, this will be 100, this will be 1000, and 2 power 10 will be 1024. Now it's more, like now 2 power n got bigger, and now it's just 24 units bigger than n cube. and log n will be this approximately 3.2. I am writing just the approximate values, it's not accurate. But now let's take n as 11. As we take n 11, the n square will be 121, n cube will be 1331, and this will be 2048, which is almost double. So the growth of 2 power n, as we see, is greater than n cube. Hence it takes lesser time, higher time. So the algorithm with 2 power n time complexity will have higher time than n cube, since the growth of this with input is higher, and this will be 3.3. So this was an example to prove that how this table works and how we can check which is lesser in time and which algorithm and or which time complexity is lesser or which will take higher or lesser time. So next we have asymptotic notations. So we have commonly three asymptotic notations: big O, theta and omega, and we usually use big O only. Big O means upper bound, theta means average bound, and omega means lower bound. Let's understand using an example. We have seen this kind of time functions. This is a linear, so it will be order of n. This one is quadratic, so it will be of order of n square. This is a recurrence relation, and if we simplify it, we can get its n log n. This one we saw in the recurrence relation, so in the previous video. So this was 2 power n. This is also kind of, if we expand this series and use recurrence relation, we can get it as maybe I guess n, and this we can get as n power n using recurrence. This is because this is a recursive function. If we simplify it, we'll get n power n, order of n power n. So this belongs to the class of n, as we saw here. This is the class of n, and this belongs to class of n square. This belongs to class of log n and log n, which is this n log n. This belongs to class of 2 power n, which is here. So the one which is lower in the height is taking higher time, and the one which is above is taking lesser time. So how do we say, what do we write, like big O or theta or omega? What should we use? So big O is upper bound, which means if there is a function whose class we cannot determine, for example this n and cube root n, its highest degree we cannot determine. So whichever is above it, the nearest class which is above it, that is n square, then it will be big O, because it is upper bound. So this function's time complexity will be big O of this function which is above it, n square. And similarly, this function whose time complex, whose highest degree we cannot determine, it can also be written as in the lower bound function. For example, the class which is just below it, the nearest class which is just below it will be omega of n, because omega, we use omega for lower bound and big O for upper bound. So in the upper part it has n square, and in lower part it has n. So, and also for average bound, which means if we can exactly determine, for example this is n square, and this will be, the graph of this function will be this only. So we can get exact class for this function. Therefore this will be theta. This we can also write as theta of n square. And here we also can see big O is also known as worst case, and theta is also known as best case. Worst case means which takes less time, and best case means worst case means which takes higher time, and best case means which takes lower time. Since the graph of this n is below it, so the best case will be it takes n, so the best case will be it takes the time function as n, and the worst case will be it will go till n square. So this region, any function coming under this region of this function will be coming under worst case, and below it every function will be coming under best case. Now let's get to the definitions of big O, omega and theta. So big O just means upper bound, omega is lower bound, and theta is average bound or tight bound, which is like exactly the same class we want to determine. So this is the similar example. In here we can see this is our f of n and this is our g of n, and this is also g of n. This is a different g of n than this one, so let's name it, or let's keep it same. For big O, we should get that f of n is less than or equal to constant time g of n. So this is our g of n for this. So this is our f of n, and we can see f of n is lower, so f of n is lesser than g of n. So we can write it as big O of n square. And also, even if it's equal, like even if we have a function f of n equal to 2n square, the graph will be this only, right? The graph will be this only, and it will be of order n square. We can still write big O because it also is valid for equals. It also is valid even if it's equal. Similarly, for omega, we can write it as like omega, the f of n should be greater than or equal to g of n, and here g of n is n. So we can also write this function as omega of n. And also, if we had a function f of n equal to 2n plus 3, the graph would be this. Then also we could have wrote omega, because omega also works for equal to. And the next is theta. Theta is a case where, like for example, we have a function f of n equal to 2n. This is our function line, and we can just determine this class. So we just write it as 3n and this as 1n. So these are two different constants, and these bounds are very tight, so it can be written as theta of n. Since this f of n should be less than constant time g of n. Here g of n is n, here our g of n is n, and this is c1 and this is c2. So f of n should be less than c1 gn and greater than c2 g of n. So here we can see that f of n is 2n, it is less than 3n but more than n. So here we can get a tight bound where g of n is n, and we can write it as theta of n. Next we have how to use these functions. Like how do we use these big O, omega and theta? We learn using an example. For example, this f of n equal to 2n plus 3. Now let us prove that we can write it as order of n. For example, first we'll just prove this upper bound. It will prove that it is order of n. So our function f of n is 2n plus 3, and for proving it as order of n, we need the definition this. So f of n should be less than or equal to constant times g of n. So we need to prove this function is less than something. So for this we will just write 2n plus 3 is less than equal to, we'll write the 2n and replace this constant term with n. So this 2n plus 3 will be less than equal to 3n. This is true, we can simply get this. We can also write any constant, but for a tighter bound we use this, like we replace the constant with an n here, and we can get something like this. So we got this, our C is 3, here C is 3 and G of n is n, so we can write it as, this is our f of n, so f of n is less than or equal to 3n, so the order, so we can write it as f of n equal to big O of n. And for a lower bound, second example, lower bound, the definition is something like f of n is greater than or equal to c times g of n. So the f of n is 2n plus 3. For this, we can simply get that f of 2n plus 3, since 3 is positive, 2n plus 3 will always be greater than 2n. So now it's simply our c is 2 and g of n is n. So since f of n is greater than c times g of n, so we can write f of n equal to omega of n, where c is 2. This is how we can prove upper bound and lower bound. And for average bound, there is a different case. For average bound, we need a definition something like this, where f of n is less than or equal to c1 times g of n and greater than and equal, f of n is greater than or equal to c1 times g of n and less than or equal to c2 times g of n. So as we found the upper bound and lower bound already, so we can use them. So as we saw, f of n is greater than or equal to 2n and less than or equal to 3n. So our c1 will be 2, c2 will be 3, and f of n is here, our f of n is 2n plus 3. So we can write f of n, here g of n is n, so f of n is theta of n. This theta represents tight bounds. It is very simple. It's just a definitive proof, like we use definition to prove something like big O, omega and theta, but we can simply, or usually we use big O because big O can be used for equal cases also. Like if we have a class which is already defined in this table, we can just use big O or omega or theta, because in all these cases the equal symbol is present and it is valid even if the cases are equal. So the last topic is best, worst and average case analysis. So for an algorithm, the best case will be when it takes the minimum amount of time. And worst case will be it takes maximum time, and average case will be it takes expected amount of time. So let's take an example to determine how this works, and we are taking a linear search algorithm for this, in which there is an array named A. The length of this array is n, and we want to find a key which is an element from this array, and we want to find its index. So this traverses the list one by one, and this will just find the key until, like, when the key is found, it will return the index, or if it's not found, it will return -1. So the best case is when it finds the key is found at the very first index, which is when the key is 10. It just compares once, because it will just compare once that if a of I, which is a of 0, is key or not. It will compare once, and so it will find the key. So in the first iteration only it can find the key. So our time function is, so it will just do one comparison. So our time function will be, let's say b of n will be 1, which is constant. So we for best case we use omega, so we can write it as omega of 1. And worst case is key is found at the last index or it's not found. For this case, the loop or the algorithm will iterate over all the elements. It will check 10, is it the key? No. It will check 25, is it the key? No. similarly it will check 30, 40 and 50. If the key is 50, it after doing all the comparisons, it will return us the index, or if the key is 60, after doing all the comparisons, it will return -1. So for this we needed to do n comparisons, because the key was at last or the key was not found, and maybe and the worst case, the time function for the worst case, let it be w of n, will be n, so it will be big O of n. So we use big O for the worst case analysis, and average case we assume that the key is equally likely to be at any place. So if the array has n elements, if the key is at first element, one comparison will take place. If the key is at second element, two comparison will take place. Similarly, if the key is at nth element, n comparisons will take place, and the average comparisons will be these sum of all this by total number of comparisons. So the sum of all comparisons will be this, and total number of comparisons performed will be n, and it will be n into n plus 1 by 2 by n, which is n plus 1 by 2. So this is our time function for average case analysis. Maybe let it be a of n, and the complexity for it will be theta of n, since we use theta for for average case analysis. So this was it for the module 1. Thank you, and if you like the video, please like, share and subscribe, and if you have any doubt, you can ask in the comment section. Happy coding. Thank you.